Okay, this is a similar problem. We have 27 degrees, 1.4 kips. Mu static is 0.13, mu kinetic is 0.08. And we want to know, is this block moving? And then draw the final free body diagram. So similar problem. Go ahead and do this one. Again, begin by finding the forces under equilibrium. Okay, so we start with our free body diagram with N and F, and we solve for the sum of the forces in the y direction equals 0, sum of the forces in the x direction equals 0. And again, this is 90 minus theta, so it's 90 minus 27, 63 degrees. And so I have this going in the y direction and the y component of that. So I have n minus 2 sine 63. I get n is equal to 1.78. Take the sum of in the x direction. I've got that, and the x component of that. So I have 1.4 minus 2 cosine 63 plus the f. I've shown it there, but it doesn't matter which direction we show it at this point. Again, I get negative 0.492, which means what? It's going the other direction. Well, what does that tell us? Remember that the friction opposes the motion or the tendency for motion. So if it's going downward, that means the block has a tendency to go upward in this case. So we're looking at that 1.4 kips potentially being able to push it upward, but we don't know. We have to find out. We need this friction for equilibrium. But can we get that friction or not? Well, I look at the static coefficient of friction, and I want to know if it's going to give me the 0.492 that I need. So, well, what do? I take the 0.13 times the 1.78, and it's 0.23 kips. Well, I need 4.92 to keep it in equilibrium, so my maximum that I can get is not good enough. So it's going to go upward. In other words, the 0.23 is less than the 0.492. So it goes upward, which means I now use mu k, and mu k is 0.08, so I take the 0.08 times the 1.78, which is 0.1424. That's what I'm going to get out of this. So the block is sliding up the ramp, and I have a frictional resistance of that much. Again, this free body diagram is not in equilibrium, and we use our sum of the forces is equal to the mass times acceleration dynamics. Okay, here's a slightly different one. It's more geometry, but actually this is not a very hard problem. So I'll go through this one as an example. What force P is needed to initiate movement in this? So if we look at what's happening here, I have a force P that's going into this wedge. As this wedge goes in this direction, and this is a fixed wall here. So what's going to happen to block A? Block A is going to go upward. So block B is going to go to the left, and block A is going to go upward. And what do I have? I have, I'm going to do the same thing I always do, which is to take free body diagrams and analyze them. So I'm going to make my cuts. In other words, I'm going to come in here, I'm going to cut around that, and I'm going to cut around that. And I'm going to follow, I got to include the force, of course. So I'm going to follow the rules that we've always done. So if I'm going to take this free body diagram, and what do I have on it? I make a cut through that surface, I make a cut through that surface, and then I've got the the 2 kilonewtons. So, and this problem is to initiate movement. What does that mean? To initiate the movement, then I know that my F's equal F max to initiate it. To initiate. So that gives me a little bit, that helps me out a little bit. So now here are notice these are my coefficients of static friction. So in other words, initiating movement, of course, is just overcoming the static friction. So so these are all mu s, and then I have surface AB, which is in here, and I have a point 2. I have surface AD, which is in here, it's 0.1, and I have surface BC, which is in here, is 0.3. So when I'm looking at this free body diagram here, I have it here, and what do I have? I've made a cut through a frictional surface here, so I have a normal and a parallel. I made a cut through that frictional surface, I have a normal and a parallel. So I don't know what those are, except that I know that they are related in a sense, because I know I have to overcome the friction. So I have my F max, so AD has the 0.1, so that means that I have NAD for this one, 0.1 NAD for that one. And since I can see what has to happen. This is moving in this direction, which means this is moving up, which means what? That means that this friction is resisting that upward motion. It's resisting the upward motion there. So this is pushing downward. Then I have this NAB here, and I have the 0.2 for this location. So 0.2 NAB. Now how do I get the direction for this one? I have to think about it a little bit. Notice that in a sense, this is moving up the ramp, which means that the friction is going the opposite direction of that. So that's the way you have to think about it. So the friction is going in this direction. In this particular case, I got to get those directions correct. Now what's happening with this block? What do I see? So I have the P here, and then again I've made a cut through that frictional surface and that frictional surface, so I have a normal, a perpendicular, and a parallel. I have a normal and a parallel. Now again, I have to be consistent. These are adjacent free body diagrams here. So I've got that one, and they have to be consistent. So this is going to the left, this one's got to be going to the right. This is upward, this has got to be going downward. And then I have the normal going upward here, because of course it's compression toward the body. And then what? This block is moving in this direction, meaning the friction opposes that motion, so it goes to the right. So that goes in that direction, like that. And then the coefficient of friction between NAB is 0.2, so this is 0.2 NAB, which of course matches that. It's got to match that. And then At this surface here, it's 0.3, so it's going to be 0.3 NBC. I can take a look at this free body diagram. I've got to get my angles correct. See, the angles were, so this is 20 degrees. So I have to get my angles correct. So this is 20 degrees with respect to the x-axis. I think we can see that. And then this one is going to be then 90 minus 20 degrees. So it's 70 degrees. So remember, all the angles are theta or 90 minus theta. So you can reason that out, why that is a 70 degrees there. So I look at this free body diagram, and notice I only have two unknowns here. I've got NAD and NAB, so I can solve this. So I take the sum of the forces in the y direction equaling 0, and I know that they're equal to 0 because I know that I'm mobilizing my full friction because things are just barely moving. So this is going to be in equilibrium. It's just initiating movement, so we say there's in essence no movement. So I get that, so just taking the sum of the forces in the y direction equals 0, what do I have? I've got that going in the y direction, that going in the y direction. I have a component of that in the y direction, and I have a component of that in the y direction. So I have four terms in this. So I've got the 2, and then I've got I've got my angles with respect to the x-axis, so that makes my life really easy here. So this is upward to the left, so it's going to be positive sine 70. And this is downward to the left, so it's going to be minus 0.2 NAB sine 20. And then I have this one downward, so it's minus. And that, I can simplify that. I get that equation. That's equation 1. Now I take the sum of the forces in the x direction. And what do I have in the x direction? I've got that in the x direction. I've got a component there in the x direction. I've got a component there in the x direction. So I have 3 terms. And so I have my NAD for that one. And then this goes to the left, so it's going to be negative. So it's minus 0.2 NAB, and it's the cosine of the angle because it's the x direction. And again, this one also goes toward the left, so it's going to be minus NAB and cosine of the angle equals 0. I reduce that, I get equation 2. I now have equation 1, equation 2, 2 equations, 2 unknowns. I can solve it, and I get NAB is equal to 2.45 kilonewtons, and NAD is 1.3 kilonewtons. So we're getting there. That's this block, okay? Now I need to do this block. Ultimately, I want the P. But I got some of my forces, so what do I do with these numbers here? Well, I now look at this free body diagram that we've drawn, and again, I take the sum of the forces in the y direction equals 0 and sum of the x direction equals 0. So we start with the y direction. What do I have in the y direction? I got that in the y direction. I got that in the y direction. And I've got a component of that in the y direction. I got a component of that in the y direction. So I have 4 terms. 1, 2, 3, 4. So taking them one at a time, I have the angles are missing here, but this is we should show those angles. And so let me just, so this is going to be, this is 70 degrees, and this is 20 degrees, so we should show those on there. And some of the this should be a negative sign also. This should be negative. And so I have that. It's a sine of the angle. And it's, so it's minus because it's going downward. So it's minus NAB sine 70. For this one, it's going upward, so it's going to be plus 0.2 NAB, and again, sine of the angle, which is 20 in this case. That's downward, so it's minus 1, and this is upward, so it's positive NBC. I already know what NAB is. I can fill that in, and I can solve that equation for NBC. It's 3.13 kilonewtons. I take the sum of the forces in the x direction, and what do I have in the x direction? I've got that in the x direction, I've got that in the x direction, component of that, and a component of that. So I have 1, 2, 3, 4 terms. 1, 2, 3, 4. So that's just a way to double check your work to make sure you have all the terms in there. And so this one goes to the right, so it's positive, plus NAB cosine of the angle because in the x direction. And then this one goes to the right, so it's going to be positive, plus 0.2 NAB cosine of the angle, cosine 20 degrees in this case. This is to the right, so it's positive, plus 0.3. And this is going to the left, so it's negative, minus P. I know what NAB is, and I know what NBC is. So the only unknown I have in this equation is P, and I can solve for P, and I get 2.24 kilonewtons. That's what it takes to move that one, 2.24 kilonewtons. So remember what we were solving for. What force do we need to push this wedge this way, which moves that up that way? And we came up with our number of 2.24 kilonewtons. Okay, this is somewhat similar in a sense, but you should be able to do this one. So I want you to try this one, homework. Again, what force P is required to get this moving? So we set it up in a similar way. Obviously, the geometry is different. The angles are okay. Then I also have this cable here, but you know how to deal with cables. So the weight of this one is 100 pounds. The weight of this one is 200 pounds. And I have this interface has 0.25 for the static coefficient. This interface is also 0.25. So, all right, so pause the video here and give it your best shot. Just, you're going to have to make a cut through the cable, by the way. Yeah, start with, start doing those individually, though. That's your best bet. Okay, so pause the video here and try this one. Okay, so let's start with the free body diagram of the top one. And what do I have? I've got the P. I've got the 100 pounds for the weight, the tension in the cable, and then I made a cut. So remember, I made my cut. Where did I make my cut? I went around here. Oops, got to include the force. And what I do, I cut through the cable, I cut through the frictional surface. So I have to put in a force for the cable, I have to put in two forces, a normal and a parallel, for the frictional surface. And then I have to put in my weight. And of course the force P. So everything is on there. And I know the coefficient of friction is 0.25, so I have my NAB and 0.25 NAB. And if this is moving in this direction, the friction is opposing that motion, so it's going to go in that to the opposite direction. I know the T is always in tension, so it's got to go away from the body. And I look at this and I take the sum of the forces in the y direction, and that's easy because I only have this and this in the y direction, so I have NAB minus 100, so my NAB in this case is 100. Then what? I take I take free body diagram of this one, and again I have to be consistent here. I guess I didn't, so the 0.25 NAB is what, is 25 pounds, so, but, you know, I want to be consistent. This is going up there, so it's got to go down there. This is going to the right there, so it's got to go to the left there. I'm also making a cut through this frictional surface, so I have a normal and a parallel, and then which direction does it have to? This is going in that direction, so the friction opposes that motion, so it's going to go to the left. So this goes to the left, so I have my NAC and 0.25 NAC for that. Again, I made a cut through the cable under the frictional surface. So I'm making my cuts around there. And so frictional surface there I made a cut through. I made a cut through that. I made a cut through my cable. So, so I have my T. I've got two forces for each of those. And then I have the weight. And again, what do? I take the sum of the forces in the y direction equals 0. And I have so I just look at these. I have these three terms. So I've got the NAB. I've got the 200 pounds going down, so it's negative. The NAB is negative. NAC is going up. Again, and then, so I know the NAB is 100. So this is pretty straightforward. The NAC then has got to be 300. Then I take the sum of the forces in the x direction equals 0. And I have the T. So in the x direction I only have these three. Angles are not difficult. I have the T. I've got, this is going to the left, so it's going to be negative 0.25 NAB. This is going to the left, so it's negative 0.25 NAC. And I know what my NAB and NAC are. NAC is 300, so I put in the 300. NAB is 100, so I put in the 100. And the only thing left in this is the T. So the T is 100, so I get that. I now know the T, so I can go back and use the top free body diagram. And if I look at this, I have this, this, and this in the x direction. Three terms, 1, 2, 3. And that gives me T in the positive. I have P negative because it's going to the left. And then I have 0.25 NAB to the right, so it's positive. I put in my values of NAB and T. And the only thing unknown here is the P. I solve for the P and I get 125 pounds. Okay, let's do another one, but now at an angle. So now do this same problem. Everything's the same, except that now I have an angle of 20 degrees here. So same thing, do the same analysis that we did. Take your free body diagram here, get some information, take your free body diagram there, then go back to the top one. So give this one a try. So pause the video here. Okay, so again, I take this. Now I have to worry about the angles a little bit. And again, this angle ends up to be 90 minus theta, so it's 90 minus the 20 degrees, which is 70 degrees. Again, we're going to, well, I guess I didn't mention it, but we always, when we have the ramp problems, take your x and y directions and like that. So again, I'm just going to take the sum of the forces in the y direction first. What do I have? I have that in the y direction, and I have a component of this one in the y direction. So this is going down, so it's going to be minus 100 sine of the angle because it's y, plus the NAB because it's going upward in the y direction. And I get NAB is 94 pounds, and then 0.25 NAB is 23.5 pounds. This is, and nothing was negative here, right? So again, this is upward to the left, so this is downward to the right. This is upward to the right, so this is downward to the left. And I'm using these, I'm using these values, so I just made that substitution right away. I have the 200 pounds for the weight of B, and then I have my T, and again, by the same logic, this is going downward to the left. This is normal to that surface. So again, you know, I have the normal and shear, normal and parallel, normal and parallel. And so now I look at this free body diagram. I'm going to take the sum of the forces in the y direction. Again, don't forget that's my y direction now. And again, this is 90 minus 20 degrees. So I have so what do I have? I've got 1, 2, and a component of this one in the y direction. So I have 3 terms. 1, 2, 3. And so I have my minus 94 because it's going downward. This is going downward, so it's minus 200 sine of the angle. This is going upward, so it's plus NBC. I solve for NBC, 282 pounds. Now I take the sum of the forces in the x direction. So now this is the x direction. And so I've got this, I've got this, I've got this, and then a component of this one. So it's 4 terms. 1, 2, 3, 4 terms. And so I've got my minus 200 cosine of the angle because its component is, you know, to the left. So it's minus. I have minus my 23.5 plus the t, minus 0.25 NBC, and that equals 0. I can put in my value of NBC. I get my T out of it. I now take that T, put it up in this. I can now use that free body diagram. So I'm looking up here, and I get my sum of the forces in the x direction. What do I have? I got that in the x direction, that in the x direction, that in the x direction, a component of that in the x direction. So 4 terms. 1, 2, 3, 4. And I've got the T, which is 162, minus the P, plus the 0.25 NAB. And then I've got this is minus the 100, and because it's in the x direction, cosine of 70 degrees. And I get P is equal to 151.3 pounds. So that is in comparison to what we got previously, which is 125 pounds. So it takes a little bit more to get it. We're pulling that B, basically we're pulling the B up the incline there. Okay, I want to say something about not frictionless pulleys, and because we're sort of in friction now. And so just so you have an understanding of what's coming up, I'm not going to go through this in a lot of detail, but this is a situation that everybody is familiar with, a bicycle. So let's see what this is. Find the forward force in this situation. In other words, I'm saying that this is moving, just moving. And what happens here? If I have, here's my pedal. So I think you can recognize this. Here's my pedal. Here's the front sprocket. Here's the rear sprocket. Here's the bicycle wheel. And now what we're doing, of course, is this, when you start pedaling, you start pushing downward like that, which rotates this front sprocket. And if you look at it, what do you find? This is not a frictionless pulley. This is not a frictionless pulley. This is not a frictionless pulley. And what does that mean for us in our problems? Well, it means that here's my chain or cable, and when we had frictionless pulleys, what did we say? We said the tension was the same everywhere. But if you look at your bicycle when you start to crank it, you'll see that when you start to move forward, the upper part of the chain will be taut and will be in tension. If you look closely, this other one, we're going to say that there's nothing in it. And so, in other words, it's loose. So I have tension here, but I have zero tension here. So completely different from our frictionless pulley systems. And if we want to get the forward force, we've got all the dimensions here. So I'm not going to, you can see that the crank is 0.7 feet, so that's that distance. The front sprocket is 0.25 feet in radius. And I have an angle of 30 degrees for my chain there. And the back sprocket is much smaller, it's 0.1 feet. And then I have a radius for the wheel of 1.1 feet right there. So let's just look at it. And what do we see? We've got, if I take a free body diagram, so I want to take a free body diagram, if you can see what I'm doing here. So I'm going to come in here, I'm going to make a cut through the chain there, cut through the chain there, and a cut, oops. I'm going to make a cut through the axle, so I have to free this up completely. So I'm going to cut the chain. It's a 3D cut. It's hard for me to show it. And then, I guess the easiest way is I'm going to cut through the axle there. And that frees that up. It's three-dimensional, so it's difficult for me to show, but I have to include, of course, take a look at your own bicycle, and you'll see that if you cut there, and cut through the axle, you've freed up everything. And so I need to put forces there. Well, I put the tension there, but I made a cut through there, but we've said that there's no tension in there, so I don't put anything. There's no force there. And what do I have? I've got my AX and my AY at the axle. I have the 100 pounds there because I have to include the forces. And if I take the sum of the forces, some of the moments, about point A equaling 0, I can see what my tension is. It's quite simple because I have 100 times the 0.7 for the pedal, and then I have, this is radius, so it's the minus the t times 0.25. So I have, this is tangent here. So again, it's perpendicular. That's the perpendicular distance. So minus t times 0.25. So I get 280 pounds. I put 100 pounds here, but I get 280 pounds there, which means what? Now I'm going to take my free body diagram here, around there, and then same thing. I'm going to cut through the chain, I'm going to cut through the axle, and then underneath the wheel. And that's a frictional surface down here. So I get my by bx there, and then what do I have there? A normal and a friction, normal and parallel, N and F. And again, I'm going to take moments about, now at the axle, point B, I take the sum of the moments about B equaling 0, and I have, again, this is, the perpendicular distance is 0.1, I have the 280 pounds, and times the 0.1. Now what do I have here? I've got my friction here. That's what gets you going. Think about it. If you're bicycling on ice, you can't get going. Why? Because you don't have any friction here. And this friction is what? It's resisting the motion. This, like I say, if you're on ice, what is this? This wheel is going to go like this, isn't it? It's going to go like that. The friction has got to oppose that. So it seems a little bit funny, but the friction opposes that spinning of the wheel, so the friction goes that direction. And if I take moments about B, what do I see? Oh, what do I see? That N goes right through that point, so it doesn't contribute anything to the moment about B. So I'm taking moments about B, all I have is the 280 times the 0.1 minus the F times 1.1, which is the radius of the wheel. So I simply solve that for F. So it looks complicated. I get F is 25.45 pounds. So I push with 100 pounds, I get a forward push of 25.45 pounds. Now, that's what we get. And of course, if we're on ice, we're not going to get that. That's when we would, I'm not going to go through it, but that's when we would compare the coefficient of friction to, what we're trying to get out of it. If we can't get that coefficient of friction, then the wheel is going to spin. So this is sort of an introduction into not frictionless pulleys and some friction at the bottom of a wheel here. I want to talk about, this is another very practical problem, the simple crank hoist. You've probably seen the wishing well, or not the wishing well, the water well, sort of the Snow White thing where you have the well here. Here's my crank, and the bucket is, there's the well. You lower the bucket into the water that's down here, and then you crank it back up. Okay, and we'll just say that the bucket weighs 100 pounds, and the crank, it has a radius of 1 foot, and again we have friction here. Friction, we're winding, and we're counting on that friction to be able to lift this bucket. So I want to, for this particular crank hoist, very simple one, for the configuration shown, which is not a frictionless pulley, what crank force is needed to lift the 100-pound bucket. So I want to look at this. Actually, I should show the AY and AX here. Let's go through those points. So let me just add that real quickly. And again, I'm going to make a cut at the axle, and I'm going to make a cut, or both of these axles, but I'll represent them as one. I'm going to make a cut through here, so that frees up that crank, and I can look at it, and I see that I have the P that I'm applying to crank this thing. I guess I don't quite show it on that, but you know how you have to turn it, so you're going to apply a P here, and I'm taking moments about point A. I've got the 100 pounds, and the radius, the diameter is 0.3, so the radius is 0.15, and this distance is 1 foot. So, what I'm doing is I'm looking in this direction here, like that. That's what this image is. So I'm looking in that direction, and my 100 pounds is going downward, and I simply take moments about point A here. So I take moments about A equaling 0, so I have the P times the 1 for that, clockwise positive, minus 100 times 0.15, and what do I get? I get P is equal to 15 pounds. So in order to lift this 100 pounds, given this configuration, I only need to crank it with 15 pounds, and I'll be able to lift that 100 pounds. Now, if I let go of this, if I let go of that P, what happens? Well, I don't put on a P, then I have this, and what's going to happen to this? The 100 pounds is not opposed by anything, and this thing is just going to spin around, and so of course that becomes a dynamic problem. But so you can see that one disadvantage of this particular system, it's very crude, you have to maintain that 15 pounds the whole time. If you don't, then this thing is the bucket is going to drop back down to the bottom of the well. So this is a very simple hoist, the most basic hoist you can have, but you can see that it still works in the sense that I can only put on 15 pounds and I lift 100 pounds. This is an example of what a different kind of hoist. I call it a neutral hoist, and you can try to make one of these at home. This is a little bit different. You'll find this a little bit interesting. I'm going to put on a frictionless pulley here, and the way that we're going to loop this thing is that I'm going to, when I put the rope or whatever on this, I'm going to wrap it around, and as I'm wrapping, I'm going to create an extra big loop here and keep on wrapping. It's hard for me to show it in 3D, because it's 3D, but what we end up with, you can try this at home, just try wrapping something, just take a pencil or something like that, and then wrap your string around it. See if I can do this. And then come in with a really big loop, and then keep going here. Oops. And keep going. So you basically have a string wrapped around a pencil or whatever, with a big loop on it, and then try connecting something to that big loop, some weight that you can clip on and serve as a little frictionless pulley in there. And what you can do is you can rotate this cylinder, the pencil or whatever, and what you'll find is that you can't lift the bucket. You can't lift the weight or whatever it is you're trying to lift. You can't lift it. But this thing will sort of move to the left or to the right depending on which way you're rotating that thing. And so that's why it's called a neutral hoist. It really doesn't go up or down. It just moves sideways. Now you might be wondering, why am I showing you this? We'll get to it in the next example. So turning the crank here does not lift the bucket, but the interesting thing about it only moves sideways. It only moves it sideways. But when you release the crank, when the crank is released, it doesn't spin out of control, and the bucket does not fall. So this is sort of leading into a different situation. So, and why is that? Because if I take and I crank this thing, like I say, it only moves sideways. But if I look at this free body diagram here, and I make a cut through the cable up here, you can, when you build this, you can see it, is that here's my free body diagram, and I should show again, I should show the AY and AX here, because we have to make a cut through that. So I still have my AY and AX, and what we find is that there's no, I take moments about point A, well, there's, sorry, let's look at this one. I let go, I get rid of the P. So I let go of it. I take moments about point A. And what do I see? Well, there's no tendency for it to rotate because these two cancel each other out in terms of rotation about point A. So when I let go of this thing, it's not going to spin. Whereas in the previous one that we looked at, I removed that P, I've got nothing over here. And now I do have a moment about point A. I let go and this thing spins around. So this sort of configuration for a hoist is pretty good because we don't want, when we lift something, we don't want it to fall out of control as it would do with this, this simple hoist. So, and now you're thinking this is pointless. So when P equals 0, there's no moment about the cylinder does not spin and the weight does not fall. Okay, so a differential hoist, so people became a little bit clever, they came up with a differential hoist whereby the only difference between this and the previous one is that I have now two diameters. I have a thicker portion and a thinner portion. And what happens is that now if I turn this crank, the weight will, for instance, if I turn it in this direction, and I wind it up on this, so now I have two different spools. So I can, if I turn this in such a way that I'm winding string or rope onto this spool, then this bucket will move to this direction, but it'll also move up because I'm going on to a bigger spool, a bigger portion. If I turn it the other way, then the string can move, or the string gets added, the weight will move in this direction and string will be added here, but it'll go down. It'll go down because I'm moving it from a bigger spool to a smaller spool. So I can actually use this differential hoist to lift this bucket. And the free body diagram of this would look like this. Now, in this particular case, we're looking at a diameter here of 0.26 feet, a diameter here of 0.3 feet, and so when I look at that same free body diagram, I have my AY and my AX there. I've got my P. This is 100 pounds. And I've simplified it a little bit. I just made these straight down for the sake of discussion. There'd be a slight angle there. But what do I have? I have one of them on the smaller, because if you look closely, look closely here, so that one support is on the smaller spool, the other one is on the bigger spool. So you have to always keep it that way. And so I have one on the outer spool, one on the inner spool, or the bigger spool, the smaller spool. And so I have 50 pounds going down there, 50 pounds going down there. And if I look at, the half of the 0.26 is 0.13, half of the 0.3 is 0.15. And so if I take moments about point A again, then what do I see? I have the 1 foot for the size of the crank. I have the P times 1, and then I have the 50 times the 0.13, and then minus 50 times 0.15, and I solve for P, it's 1 pound. So I can actually lift this 100 pounds now with just 1 pound. Now I have to crank it a lot to get it to move up, but this little clever device will with a very small P, I can lift this 100 pounds with this differential hoist. So now when I look at this, if I take away this P, so let's get rid of that P, what do I find? Well, it's a small moment. It's a small moment. And with a little bit of friction, you can throw in some friction there, you can resist that small moment that this produces, because you get, it's just the difference. They're still opposing. These two are still opposing each other, and so this particular type of hoist is, with a little bit of friction in the system, is not going to rotate and drop the load. So it has two advantages. One, it's not going to drop the load, and the other is that it takes a very small load to lift something quite heavy. So, and then somebody clever also said, oh, this is a more complicated one, but it's the same idea. This again is the differential hoist. I'm not going to go through this in a complete detail, but it's the same thing. You've got the differential hoist with the two different spools here, and then instead of using a crank, if you just take and put a continuous, again, you can build this at home and try this out. If you put in a continuous frame with sprockets and things like that, now we need sprockets and stuff. It's a little bit different, and I got a frictionless pulley down here, but you can, instead of cranking it, you're pulling here, which rotates this. So instead of the crank, you're pulling here, and you can create something similar with this, and now you need a little bit more force. For these particular numbers, you end up with 6.67 pounds. This person has to pull with 6.67 pounds to lift that. But this is closer to the way an actual hoist will work. It's the same principle as this differential hoist. It's just that we've got now two things. We just have what's called a continuous chain, and then instead of a crank, you're pulling on it. Okay, I will stop there.